Okay, so I'm going to do the talk now. So this is the talk on Introduction to Reverse Engineering. We'll be doing a follow-up session on binary exploitation and memory corruption and stuff like that later on, but not now. Um, this will be a sort of brief overview, well, rather long overview of how things work on a computer so that we can go into that stuff. But this should be enough to solve many CTF challenges until that point. So give me a second. I'm being spammed on Discord. I'm just going to have to close that. So, what is reverse engineering? So, engineering is when you design something to achieve some form of purpose. And so reverse engineering, as you probably expect, is doing the exact opposite of that. It's taking something apart to work out what it was designed to do. This can be compared to real-world science, but instead of applied to the natural world, it's applied to human design systems. So just like how a doctor dissects human bodies to determine the function of various organs, or how particle physicists smash particles together to determine the behaviour of larger systems, we can have a look at computer chips to analyse what they do, or we can look at, in a sort of more fundamental sense, we can look at crashed planes and examine how things go wrong with their design and construction so that we can stop them happening again. But we're not talking about sort of extreme important stuff like that. We're going to be looking at software, specifically compiled and assembled software, which is known as binaries. These include executables and libraries. The thing we are looking for, the purpose, is the behaviour of the program. And in this talk, I'm going to be looking at the x86 and x64 architectures, which basically means all laptops and desktops you're going to come into contact with, except for things like mobile phones and Android and iOS tablets. But you probably won't be looking at those with, extreme software too much. So, why does anyone actually care about this? A large amount of software that is part of everyday life is actually stored as a binary. This includes pretty much every modern game, because compiled code is pretty much always faster. Software such as web servers, SSH daemons, SMB file shares, and shells are again always compiled pretty much. I mean, there are some exceptions, but even languages such as Python and Java actually need to run at some point on a physical machine. And so at a base level, they exist as binaries on your system. And the most powerful piece of code on your computer, which has complete final say over what goes on, is your kernel. And that's made of a mixture of C, C++, and assembler, which of course therefore exists as a binary on your machine. The source code that the binary is created from tells you what the program does. And the computer does what it was told to do by the source code. And so, therefore, this information must exist somewhere in the intermediate binary, which is actually run by the computer. So let's actually look at that creation process. Oh, whoops. A compiled language, such as C, is parsed and turned into some form of intermediate language. We don't need to know too much about this step, as it's very, very complicated, and it's one of the oldest research topics that is still heavily worked on today. As such, I probably couldn't do it justice without months of lectures, and I don't know enough about it to do that. There's probably a module that you need to do that. Anyway, this intermediate language is turned into a language called assembler, which is pretty much a one-to-one correspondence with the actual instructions sent to the CPU. Assembly, this language, has no concept of functions, data structures, variables, or even portability, making it incredibly difficult and repetitive to write complex programs in it. But you can, if you want to, actually do this. You can write programs in assembler. And until rather recently, 30 years ago, this was actually the main way of writing fast code, until compilers for languages like C actually got to the point where we could get the performance gap close enough that the lack of data structures and variables and stuff became worth doing. So let's see what else. This assembly then is turned into machine code, into a sequence of ones and zeros. And these are the electrical signals that are actually sent to the processor. And are a large part of what give binaries their name. Of course, reading this actual sequence of ones and zeros is incredibly difficult. In fact, I'm pretty sure there doesn't exist a single person on the planet who can decode all of the x86 architecture, let alone understand what the instructions do. However, luckily, because we have this one-to-one-ish relationship with assembler, we can undo this conversion into machine code, into assembler, which, whilst not easy to read, can give us a lot more understanding than just a sequence of numbers on the screen. So we'll try and do most of our work with assembly rather than the machine code. So machine code is rarely stored in its raw form. In fact, it usually only happens for like the first few microseconds of your computer startup time when it boots. We generally write our code inside of an operating system to be run by the kernel and by the various bits of executable lying around on it. And programs generally don't just loop for a bit either. They're definitely not just code. They also have a bunch of data on the side as well. And they also have a point where the code starts, which is called the entry point. And all of this needs to be kept track of somewhere in a big file. This file is generally what we refer to as the binary. I won't go into too much detail about the processes of creating this, compilation, linking, and dynamic linking. All you need to remember are executable files are the files that are run directly, like .exes on Windows. Libraries are a bunch of code that is compiled and kept for later, which is split into dynamic libraries, which are dynamic libraries which are loaded at runtime, and static libraries, which are actually compiled into the executable. So, these files have many different formats. These formats are known as executable formats, which is also very confusing because they're also used for libraries, but there you go. So the original format that pretty much everything is based off these days is called a.out. Now, we don't use this format much anymore, but when I say based off, everything sort of descended from this. In fact, you can actually see this, that with any compiler you use on Linux or Mac or BSD or anything like that, if you don't specify an output name for the program, it will default to a.out, because way back in the mists of time, that was the format they all used. The second one you probably heard of, PE binaries, portable executable, also known as XEs or DLLs, are by far the most common format on Windows. .exes are executables, .dlls are dynamic libraries, and .libs are static libraries, though on Windows static libraries aren't really used. Com binaries are an old DOS format, and basically are only now seen for when someone accidentally uses a URL for a file name, or actually as a poorly known format for viruses, so that people don't realise it's executable. ELF is the most common Linux and BSD format. It's pretty much universally used. It's very difficult to get anything else to work on it. It's probably the most complex format. It has many different features for working across large numbers of platforms. And executables don't have a file extension. .sos are dynamic libraries, and .as are static libraries. And the final one, Marco, yes, I have pronounced and spelt that rightly. Right, sorry. Is the format used on macOS. Executables, again, don't have a file extension. Static libraries, again, end in .a. And shared objects or dynamic libraries end in .dylib. These formats have, whilst very different in their actual construction, have the base ideas are the same. They have they are split into a bunch of sections. .text holding the executable code, which is a very confusing name. It doesn't hold text, it holds code. .data, .ro data, and .rdata actually hold the data themselves. .data is the writable one, and .ro data and .rdata on Windows are the read-only ones. The stack and heap sections are created at runtime for dynamic memory allocation. We'll go into this in the binary exploitation talk later on. You don't actually need to know too much about this now. And of course, there are many more sections, but these ones here are the most important ones to keep in mind. It also contains something called the symbol table. And the symbol table is a bunch of names for functions and variables that can be used for libraries. And this is probably the most useful piece of information in the whole of reverse engineering. Just knowing what the functions are called can tell you so much about their purpose. Now, all of this is very nice, But we actually need to be able to read this information. So, like many difficult problems, we can cheat with abstraction. So instead of actually looking at the assembler and the code beneath it, we can look at the variables, the symbol tables, and the control flow. If we fail with that, we could try using tools to guess the original code. Unfortunately, these tools aren't perfect, as we lose all the comments and pretty much all the variable names with compilation. The compiler also often rewrites bits of the code to make it run faster, which can make it very difficult to understand what it was originally intended to do. And decompilers are automated, and so sometimes their solutions are incredibly convoluted and confusing, and make it even harder to understand than just the assembler itself. And so if all else fails, we just have to try and understand the assembler. It's a real pain to do, so I'll only briefly cover it, and frankly the other tricks work well enough on CTFs for me that I generally don't even have to look at the assembler too much, so I'm not really an expert on it either. So static variables are the easiest things to handle. You really don't need much to do this. The variables are located, as I said before, in the .ro data, or .r data on Windows, and .data sections of the executable or library. Things like text, so message prompts, things that will pop up on the screen. This is often just a bunch of characters followed by a null. And there exists a tool on Linux called Strings that will try and find these things for you. It should be installed by default on Kali. And you can solve, I guess, probably about half the CTF challenges based on reverse engineering with just this tool. It's very, very useful. Numbers and bytes are a bit more difficult to find because they're very difficult to distinguish from the actual instructions, and most of it is just useless garbage. So you need to look at the assembler and look at the variables it's referencing before you actually do something, before you actually go and start reading through all the data. This will involve looking at the assembly a bit more. So symbols, there's not much to say about them, but these are probably the most useful tool in reverse engineering. As mentioned before, this is a list of names for memory addresses of functions and variables in the file. These are used so that programs can look up functions and variables in libraries when it's trying to load them. And they're viewable in Cutter, which is a tool I'll be demonstrating later. So if we can't get what we need from all this data and metadata, we're going to actually start needing to look at the code. But just before we start reading the assembler, we can make it easier by looking at its shape. Jump instructions generally begin with J, JMP, JLE, JNE, and so on, and fall into two categories. JMP jumps to an address. It's like a go-to. Well, it is, in fact, actually on most systems, it's implemented as a go-to. It doesn't ask any questions, it just goes to a place in the memory. All other jumps are known as conditional jumps. They'll be based around some form of condition. You can look up each instruction to see what they do. So JLE is jump if less than or equal to, JNE is jump if not equal, and there's a bunch more. These are generally used to handle if statements and loops. And function instructions, calls a function, is like a jump, but it saves where it came from. And ret goes to the instruction after a call. So it will allow you to go back to where you came from, just like a normal function call in Python or C or whatever. Most disassemblers, like Cutter, will look up the addresses in the symbol table to give you the function's name, which is very useful for working out what they're doing. Okay. Decompilation, as I said earlier, attempts to recover the original source code. Cutter uses Ghidra's decompiler, Ghidra being a tool developed by the NSA for malware analysis and for hacking. It's very, very useful for very simple functions, but often can get the type of variables wrong. It can also create horrific spaghetti code that just makes no sense whatsoever. But if it does work, you don't have to read any assembler at all. You can just look at the decompilation output and you'll be able to understand exactly what it does. So let's start on the fun bit, reading assembler. Most of this will probably go over your head unless you've done some low-level programming, but if you rewatch the video and practice a lot, you should be able to get most of this. The bits that don't go over your head will be very useful, not just in reverse engineering and CTFs, but actually in your general understanding of how computers work. I'll be using the Intel syntax here rather than the less popular and Sigil-oriented AT&T syntax, which is just nasty. This means that op in square brackets means instead of talking about the value op, it's talking about the position in memory with address op. Instructions with two operands or arguments generally put the results of the operation in the first one. Think of this as like x equals some function with arguments x and y. Everything about the names of registers and instructions is very, very CPU specific. So this information will not apply to ARM CPUs, which mean your phones and tablets, or if you're using Motorola 6800s or something, it won't work. But for the vast majority of systems you will come across, it will. This is why porting assembler is so difficult, because understanding in one doesn't necessarily translate to understanding in another. And this is why we generally use programming languages to abstract it away. So unless otherwise obvious, a 2 or 3 letter operand is generally a register. A register is a tiny, tiny piece of very fast memory in the CPU. And when I say tiny, I really mean it. It's about 8 bytes big. Registers that have a full name that is 2 letters long are rarely used and generally can be ignored. Often these things are sort of left over from an older version of the CPU and kept in for compatibility reasons. Or handle specific things like stack cookies, which are complex and not within the scope of this talk. The first letter of the register tells you how many bits of the register should be used, R meaning 64 bits and E meaning 32. In general, 32-bit computers can only use 32-bit registers, whereas 64-bit computers could use either. Most registers are general purpose, which means you can use them for pretty much anything. Exceptions to this, the main exception to this being SP and BP, which are stack pointers, which will be explained in a later talk. You'll see SP and BP, of course, with RBP or ESP or something in the code with one of the prefixes. Registers beginning with XMM and YMM are used for floating point numbers. This probably won't turn up too much in any code you're likely to reverse engineer, as floating point generally isn't too important unless you're looking at financial code, or I suppose low-level game logic. So here are some basic instructions for assembler. If you don't know an instruction, there's always extensive documentation on the internet you can use to look it up, but it's quicker to keep some of the basics in mind so you don't have to keep doing that. If you can, skip the instructions you don't understand in a binary, as most of them do very boring caretaking jobs, such as making sure there's enough space for variables or preparing for function calls. This is actually this caretaking stuff is actually rather interesting in some specific cases, as I'll cover in the binary exploitation talk, but generally can be ignored if you're trying to work out what the code generally does. Anyway, here's a couple of them. Mov op1 op2 sets op1 to the value of op2. It's the same as writing in Python op1 equals op2. LEA op1 op2 sets op1 to the address of op2. So this can be used for pointers and stuff in C and C++. Add op1 op2 adds op2 to op1 and then puts result in op1. Sub, mul, and div are basically the same as add, but of course do subtraction, multiplication, or division. The final important one is comp, which performs a comparison between its two operands and is used for conditional jump instructions. So, like we said earlier, the where's I to put it? Yeah, the JMP, JLE, JNE stuff all requires a comp instruction before it to tell it what it's comparing. So, sometimes the binary just doesn't do what you want, no matter what you do. If you had the source code, you could just rewrite and recompile it, which is one of the reasons why open source software is so useful. But you don't always have access to the source code. There are two main ways of doing this. You can jump over code, so just skip out the stuff that does stuff you don't want, which is you can just replace with a jump. So if you've got, a bunch of addition instructions that take hours to run, you can just change the first one to a jump to the end of the addition instructions, so you don't have to go through the whole hassle. And you can change a jump condition. So if you want to check a password is equal to something else, you can change the condition to check if it's not equal. And then as long as you type in anything that isn't the password, it will let you straight through. And this is great for bypassing login prompts, and has also been used for bypassing DRM and stuff like that. Obviously, I'm not allowed to condone such actions. Most tools like Cutter can do this rather easily, as I'll be demonstrating in a minute. So let me open up the demonstration. Can you see this? No. Can I make this big? There you go. So I have a quick C program here. I can put it somewhere else if it makes it easier. But basically, it sets X to 4. It prints out some stuff. It calls a function that just prints out more stuff. Sets X equal to 5. Prints out more stuff. X equals add 5x. If X is equal to 6, this won't be called. This will be called. All this. It's a standard, very basic C program with a lot of printing functions in it. If I can make this on the... Oh, that's not good. There we go. So I've compiled it, and hopefully... So this is Cutter. It does a bunch of reverse engineering stuff for you. You can just invoke it, if I put this bigger, as Cutter and then the path to the executable. In this case, it's RE. It will present you with this screen. Just click OK. The defaults are pretty good. So I'll make this full screen here. This is going to be quite small. Is there any way I can make it bigger? That doesn't help. Okay, I will try. Oh, I could switch screens. Yeah, give me a second. Move OBS and you. Give me 1 second. I just need to switch over the screen. Yeah, that's right. Cool. So you should be able to see that slightly better now. So here you see a bunch of symbols. This is where the symbols are dumped. Here you can see the decompiler result. And here I've selected the graph, which just gives you a brief overview of the control flow, which we were talking about earlier. So the first function that gets called that you care about is main. And this is true for any program, basically. If I switch over to it, you can see the decompilation here, which is pretty much the same as the source code we had. Let me make this smaller. Which is pretty much the same as the source code we had here, if you look. So, this is a bunch of useless stuff that just sets out. This load RDI. RDI, in this case, is the first argument to any function, call puts. So you can see what this does is it prints the string. This is printed to the string. This prints the screen, the text. This is printed to the screen. In fact, you can see that's what it's decompiled it into. And then it's printing calling subroutine, and then it calls the subroutine. And we can look at, it says we are now in one of our subroutines. It returns, printing some more stuff, all this lovely stuff here. It then, this is the comparison thing here, the if it equals 6, jump if it, so yeah, compare it to the variable, which is renamed x to var 8h for some reason. Compare it with 6, and if they're not equal, go over here. If it is equal, go over here. Either case, once that's done, it goes down to this bit of code here, which goes down to this bit of code here, which does a comparison. This is the less than, which is for our for loop, if I can bring my code back. Here, this is the I less than 10 bit here. It compares it to 9, and then jumps if it's less than or equal to. Because of course, if something is less than or equal to 9, it's less than 10. So move it. If it is if it's not less than or equal to, it returns, so finishes. Otherwise, it goes through this loop and prints again. So if I run this program, I'll do it over here with a little thing here. Should print out a bunch of stuff. It prints out, this is printed to screen, calling subroutine from here. We are now in one of our subroutines from here. Call puts back from subroutine here, adding 5 to x here. This will be called here, then does the for loop, printing out all numbers from 0 to 9. Now, let's for a second imagine that instead of saying this will be called, we want to change it to say this won't be called. So we can change this jump if not equal to instruction to, if I can edit instruction, we have in write mode, I can change that, so instead of being jump if not equal to jump if equal to. So I write that, the decompiler has changed it around, so if it equals 6 it prints this will be called, and if it doesn't equal 6 it'll be this won't be called. So now if we run the program again it won't work. Okay, let me close cutter. Actually, can I run it? Actually, I think I can run it in here. Please. This will think for a bit. I don't think you can sudo apt-get install cutter. You have to. I think we've got a link for it on the Cybersock website. Right, there you go. If I just there you go. So it's put the output here for some reason. If it'd like to actually load, please. Yeah. So notice how instead of saying this will be called, it says this won't be called. It switched over the if condition. And you can imagine that, in this case, that's not actually desperately interesting. But if you care about the, for instance, this could be a password check function, or it could be something that gave you the flag, and it might decide not to give you the flag, but you could change it to give you the flag. It's very nice. For this, for instance, so imagine we wanted to jump over all of this calling subroutine back from subroutine stuff. We could change this instruction to edit instruction. Well, okay, so we have to calculate an offset here. Okay. So I could, let's see, we want to jump to, yeah, imagine we just want it to stop just after it says calling subroutine. We can get the address of the return function here. So the return instruction here, if I can get the address, there we go. I can open up a calculator just quickly. I can just go. Ah, dear. Can I put this in? Yep. So x86 uses relative addressing. So you actually have to, instead of giving an absolute address to jump to, you actually need to say how far forward you have to jump from the next instruction, just to be confusing. So we did the puts here. So copy address and give it in hexadecimal. So we want it to jump forward 8A. So if I go to the this instruction here, edit instruction, we want to say jump 0x8A. It doesn't like that. Why is it not like that? Oh, is that gonna... No? Okay. Why are you not working? Oh, that's bad. Okay. Let's see. Calling subroutine. Of course, it never works first time. Okay. Well, that doesn't seem to be working. Okay, fine. Instead of calling puts, then I'll get to call main again. So put it in infinite loop. So we can call, if I can copy address, call puts, edit instruction. There you go. So hopefully that probably will crash, but we'll see what happens. So I'm going to run it again. Yep, there you go, it crashed. If I can get the output somewhere, please. So it's going to think for a second. Oh yes, it's because I'm running big. It should be fine even if I modify. Ah, there you go. So yes, you're right. So I didn't actually edit it because I was running the program. You're right. Thank you. Sorry about that. That's just stupid of me. Yes, you see, it keeps reverting because. Right. Okay. So calling subroutine, call puts. So instead of calling subroutine, we'll get it to call main. So. Oh, that's a good point. Oh, it does not like that. Oh, right, yes, of course. Sorry. Remember, it's relative, so we want to call main relative to the next instruction. So, copy address. Copy address. So we need to go back 31 bytes. So why is it not working anymore? Fine. Okay, I'll just put a jump back to main then. So this will just keep looping this code over and over again. Notice how we've got some random stuff after it because it doesn't care about what happens after it because we just modified this instruction and that's messed up the bytes after. So if I run that again, hopefully it will think for a bit. Why did demos never work first time? Is it crashed? Quite possibly. Yep, that's crashed. Okay, just take my word. Oh, wait, no, it hasn't crashed. There we go. If I could just, yeah, there you go. We now have an infinite loop. If I can put that over there and put cutter over there. What's happening, if I go to the graph. Oh, it does not like that. It's just looping the print to screen thing over and over again, and then going back to main. So it calls that and goes back to main over and over and over and over again. So there you go. That's a fun thing you can do with it. And of course, you can imagine that if you've got a password check or a DRM check or something like that, you can just jump straight over all that code. Obviously, there were counter measures against this, but you know, this is a basic introductory talk. Right, okay. I'll stop the program now. But yeah, okay, well, I think that should be enough as a basic introduction. Sorry if I'm a bit tired at the moment, so sorry this isn't the best talk ever given at Cybersock. We have some CTF challenges up. The first two Pwn challenges are two reverse engineering challenges you can do. We're actually currently writing another one, so that should be up in about half an hour. But yeah, thank you very much for listening, and see you in Discord.